Today we're starting section 3.1, which is dealing with functions in our introduction to functions. By definition, a function f is a rule that assigns to each element x in a set A exactly one element called f of x in a set B. What that means is when we have this function, we have input values, and these input values are all what we would call x values, and they come out of set A. And then when we apply the function, we're going to get output values, and these values we represent as f of x, and they come from set B. And again, remember that a set is just a group. So it's a group of numbers that will be in set A, and it's another group of numbers that will be in set B. When we see this f parentheses x, that's read f of x, or the value of function f at x. It's not f times x, which is probably what you're used to doing when you see parentheses. By the context, that's function notation, and it's f of x. The domain is the set of all the x values from set A. In other words, these are the input values, the values that will be put into the function. On the other hand, the range is the set of all the possible values of f of x as x varies through the domain of f. What that means is, as you put all the different values of the domain into the function, and you get all the answers back out, all those answers, the output values, all those answers are put together in a group, and that group is called the range. So the range is really just the set of all the possible output values, and those output values, again, as we mentioned before, are represented by f of x. The independent variable is a symbol that represents an arbitrary number in the domain. So all that means is it's the x values. It's the x as the independent variable. When we talk about the dependent variable, that is a symbol that represents a number in the range. This can be viewed as or represented as the y, or a lot of times with functions we represent it as f of x. Many times functions are hard to understand, but one way that we can think of functions is that they are a machine, like a function machine, and then it changes each input value in a specific way to produce the output value. That's one way of thinking about it. The machine always does the same thing, and then depending on what you put into it, you get something different out. Another way of thinking about it is that a function is a set of directions that tell you what mathematical operations to perform on an input value. And then, of course, depending on what input value you put in, we'll get a different output value out of that set of directions. When we talk about functions, one way that we can represent them is by drawing an arrow diagram or a mapping diagram to show what numbers are mapped to what other numbers. And this is a diagram in which each arrow connects an element of A, the domain, to an element of B, the range. So if you look at this example, we can see that -2 gets mapped to -4. -2 also gets mapped to 1. When we look at the 1 in the range or in the domain, that gets mapped to -2 in the range. 3 gets mapped to 2, and then the 3 from the domain also gets mapped to the 3 in the range. We'll talk about this a little bit more later on. This is a relation. It actually ends up not being a function, but again, don't worry about that right now. We'll talk about that later. When we think about the domain, we have two different types of domains that we want to consider. And the first is an explicit domain. This is a domain that is clearly stated. For instance, if I said that we were going to take a certain function and we were going to have the domain, and I said the domain is all the integers. Well, that is an explicit domain because I'm telling you exactly what the domain is. The other type of domain is called an implicit domain. And this is a domain that contains the set of all real numbers such that the expression is defined as a real number. One example of this would be, for instance, if my function was 1 divided by x. I can pretty much put in any number for x that I want to, with the exception I can't put in a 0 because 1 divided by 0 is undefined. Another example where we have problems is when we talk about radicals, because we can't take the square root of a negative number. That's not, that doesn't give us a real answer, it gives us an imaginary answer. So those are the two biggest issues that we have, is when we have fractions, the denominator can't be equal to 0, and when we have radicals, we are not allowed to take the square root of a negative number. For the first example that we'll do together, we've got f of x equals the absolute value of x. We want to evaluate f of negative 6, f of 7, and f of 0. So those are our input values, the negative 6, 7, and 0. Then we're going to state the implicit domain and range of this function. And finally, for part C, we're going to draw a mapping diagram for these three values. In example 1, part A, we are supposed to evaluate three different values using the function f of x equals absolute value of x. The first one is f of negative 6. And all we do when we're evaluating a function is, if you remember, our x is the generic input value for the function. So we're going to use a specific input value of negative 6. So we just take the absolute value of negative 6, and the absolute value of negative 6 is 6. So we do the same thing for f of 7, and we take absolute value of 7. And that gives us absolute value of 7 is 7. So f of 7 for this function is 7. We do the same thing lastly for f of 0. We just replace that generic input value of x with a 0, a specific input value of 0, and the absolute value of 0 is 0. The next part of the question asks us to identify what the implicit domain is. And when we're dealing with implicit domains, remember our domain is everything that is defined for this function. And so if we think about it, absolute value of x, we can take the absolute value of any number. So our domain, our implicit domain, is simply all real numbers. Or you may see it written as x such that x is an element of the real numbers. That's written in set notation. The range, on the other hand, for this, if you think about the values that can come out of this function, if you take the absolute value of something, you will never get a negative number. And so our absolute value function for the range, we're going to have y such that y is greater than or equal to 0. And again, the reason for that is we will never get a negative number out of a function that's written like this with the absolute value function. So our range is, our domain is all real numbers, but then our range is simply positive numbers and 0. For part C, we're supposed to draw a mapping diagram using these three values. So for our mapping diagram, we place the values from the domain right here. And I'll just use this oval here. We've got negative 6 and 7 and 0. And then we place the values for our range over here. We can see that our output values were 6, 7, and 0. And then the mapping diagram just draws a picture of showing what these functions get sent to. So if you look at this mapping diagram, negative 6 is mapped to positive 6, 7 is mapped to 7, and 0 is mapped to 0. When we evaluate functions, and this can be a little bit tricky at times, but when we evaluate functions, we want to think about x acting as a placeholder for the input value. So a lot of times when I read a function, I'll say, let's say it says f of x equals 3x plus 2. So I'll think of 3 times the input value plus 2. And that just reinforces that that x is just holding the place of our input value. So let's take a look at example 2. We're given that the function is 5x squared minus 2x minus 3. So we're going to evaluate f of negative 3, f of 0, f of 2, and f of 1/2. As we look at example 2, we are again given a different function, 5x squared minus 2x minus 3. And in this case, we're given other values to use. So again, x is our generic input value. we are given a specific input value in part A of -3. So we're just going to replace all the x's with -3's. So as we simplify this, this is 5 times 9, -3 times -3, plus 6, 2 times -3, and then -3. And that gives us 45 plus 6 minus 3, which is 48. For the f of 0, again, we do the same thing. Our input value is now 0. Well, 0 squared is 0, times 5 is 0, minus 2 times 0 is 0, minus 3. So that one gives us -3. When we plug in the 2, again, we're replacing the generic x input value with a specific input value of 2. So 5 times 2 squared minus 2 times 2 minus 3. So that gives us 5 times 4 minus 4, 2 times 2 minus 3, and that is 20 minus 4 minus 3, and that is 13. And then finally we have 0.5, and so we have, for our new input value, so we have 5 times 0.5 squared minus 2 times 0.5 minus 3. And again, we just evaluate this. 0.5 squared is 0.25 minus 2 times 0.5 is 1 minus 3. 5 times 0.25 is 1.25 minus 1 minus 3, which gives us negative 2.75. So those are our values for this function. Again, the key thing to remember is when you're given a function, this x right here in the function just counts as a generic input value. And then when we have f of something, -3 or 0 or 2 or 0.5, that is the specific input value that's going to go in place of all of those generic input values labeled as x.
In example 3, we've got a cell phone company that charges $39.99 for 450 minutes of calling and 45 cents for each additional minute. And we want to describe this situation with a function and then find the charge for 100 minutes, 400 minutes, and 480 minutes.
In example 3, we're given a situation about a cell phone company that charges $39.99 for 450 minutes of calling time per month, and then 45 cents for each additional minute. So the first thing we're supposed to do, or we need to do, is represent this as a function. So we're going to call this f of t, since we're dealing with an amount of time. And if you notice, this is a piecewise function, because if we use any amount of time on our cell phone plan less than 450 minutes or equal to 450 minutes, we pay a total of $39.99. So this function is a piecewise function, and it equals $39.99 if t is between 0 and 450. Okay? Now, after that amount of time, then they begin charging you extra amounts of money. So, we know that for greater than 450 minutes, what we have to do is we have to pay that $39.99, because we pay that no matter what, and then plus 45 cents for each additional minute. And the question here becomes, how do we represent each additional minute? Well, we know we've already paid for the first 450 minutes, so then for each additional minute, that's going to be the amount of time minus that initial 450 minutes that we have already paid for. So this second part of the piecewise function is that t is going to be greater than 450 minutes. So notice again, if we use any amount of time between 0 and 450 minutes, we pay $39.99. After that, though, we pay the initial $39.99 plus 45 cents per minute after that 450 minutes. Okay? So, for instance, if we used 500 minutes, we have to pay $39.99 plus 45 cents, and then 500 minus 45 is 50, so that's for that additional 50 minutes. Now, once we have that function, if we go back and we ask, okay, what is this function for 100? How much do we pay for 100 minutes? Well, again, that 100 minutes is included already in our $39.99. So our charge for 100 minutes would simply be that monthly fee of $39.99. The same is true for the 400 minutes because we've already paid for the 450, so the charge for 400 minutes is $39.99 again. But in this last example, we're supposed to find the charge for 480 minutes. So we know we've got the $39.99. That pays for the first 450 minutes plus 45 cents times, well, we used 480 minutes. We've already paid for 450, so we have an additional 30 minutes that we have to pay for. So $39.99 plus 0.45 times 30, okay, $39.99 plus 0, and if we multiply this out, looks like $17.50 more. So that gives us a total of $57.49 that we are going to have to pay if we use 30 minutes more at that rate. Again, that rate is probably a lot lower now with the new cell phone plans, and you probably get a lot more than 450 minutes. But using this plan and this information, we get $57.49 if I did my math correctly. And I obviously didn't do my math correctly because 45 cents times 30 isn't $17.50, it is $13.50. And so that's going to make it $53.49.
In example 4, we are given that f of x is 4x squared minus 2x minus 3. We will evaluate f of a, f of negative a, f of a plus h, and then this quotient, which is f of a plus h minus f of a divided by h. And of course we can't let h be 0 because that would make it undefined.
In example 4, we're given another function, 4x squared minus 2x minus 3 is equal to f of x. And again, x is a generic input value. So when we want to find out what f of a is, we simply replace that generic input value with an a. So we get 4a squared minus 2a minus 3. And we want to check this, is there any more simplifying that we can do? And in this case, there isn't, so we just leave it. When we evaluate f of negative a, again, we replace that x with a negative a. So we get 4 times negative a squared minus 2 times negative a minus 3, and that gives us negative a squared is just a squared, so it's 4a squared plus 2a minus 3. And then this part C here takes a little bit more work because, again, we're replacing that x with a plus h this time. That's our new input value. That is squared. Minus 2 times a plus h minus 3. Well, that means we have to multiply a plus h out. And a plus h squared means a plus h times a plus h. This part we can just distribute. We get minus 2a minus 2h minus 3. And so we have to FOIL this out. So the 4 stays here. We get a times a is a squared plus a times h plus a times h again plus h squared. And then we have minus 2a minus 2h minus 3. And then finally, we distribute the 4. Now notice these two together is 2ah. So when we do this, we get 4a squared plus 8AH plus 4H squared minus 2A minus 2H minus 3. And that is f of a plus h. The last thing they ask us to do is this problem right here. F of a plus h minus f of a divided by h. This is actually what we call a difference quotient. But fortunately, we've done most of the work already. F of a plus h, we just did. That's this thing. So I'm just going to take that and put it in right here. 4a squared plus 8ah plus 4h squared minus 2a minus 2h minus 3. And that is the first piece. So I'm going to label that as the first piece. And I think I'm going to have to move my camera here. And then we have minus f of a, which we did that already also. That is 4a squared minus 2a minus 3. And that is all divided by h. Again, the one limitation is h cannot be 0, so that because if h was 0, we would have it be undefined. But notice what happens. This looks really long. It looks like a big mess, but let's notice what happens. This negative distributes through the parentheses here. So that becomes a change it. That becomes a negative 4a squared, a positive 2a, and a positive 3. Now as we look at this, positive 4a squared will cancel with negative 4a squared. Negative 2a will cancel with positive 2a. And negative 3 will cancel with positive 3. So everything in that second set of parentheses cancels, and here's what we're left with. 8ah plus 4h squared minus 2h over h. And if you think back a couple tests ago, notice there is a common factor here. There's an h, and actually a 2 also, in every one of these. So we can factor that out. 2h. This leaves us with 4a plus 2h minus 1 over h. Well, now that this is multiplied, this is a factor, this h can cancel with this h, and we're left with 2 times 4a plus 2h minus 1. Now, of course, if we wanted to, we could distribute that out and get 8a plus 4h minus 2. And I don't remember how I did it on the PowerPoint, but this would be our answer for this difference quotient.
In example 6, we're going to identify the domain, the implicit domain for the following functions. And remember, we do that because we can't let the denominator be 0, and we can't have negatives inside of our radical.
In example 6, we are asked to find the implicit domain for 3 different functions. And if you remember, implicit domain means it's all the numbers, all the real numbers that are defined for a function. So this really kind of gives us a good list of the ones that have problems. We cannot, again, in a fraction, we can't let the denominator equal 0. So as we're dealing with this one, the way we set it up is we don't let the denominator equal 0. So this is a quadratic. We can factor this. And we find out that x and x go there, and then the signs are the same because they have to multiply together to be a positive 2, and they're both negative. And the only factors that will work are 2 and 1. So then we find out, setting each of these not equal to 0, we find out x cannot be 2 and x cannot be 1. So probably the easiest way to write this, as long as we've got it written like this, is in set notation. So we have the set of all x values such that x is not equal to 2 and x is not equal to 1. So that's our implicit domain for this. You can use anything except for 2 and 1. Now looking at g, we have a radical. And if we remember, we can't take the square root of a negative. So we have 4 minus x squared has to be greater than or equal to 0. That way, the stuff in here won't be negative. Because if it's negative, again, that's undefined. So probably the easiest way to deal with this, if you remember back to our test in chapter 1, we can again factor. So 4 minus That's not what I want. We can factor this as 2 minus x and 2 plus x. It's the difference of squares. It has to be greater than or equal to 0. It has to be positive. So again, we can set up our intervals. When does this one equal 0? It equals 0 when x is 2, because 2 minus 2 will be 0. This one equals 0 when x equals negative 2. And then what we need to do is we need to check our values and see. So if we pick, if we're looking at this one, let's just pick a test point this time. If I pick, for instance, negative 5, 2 minus negative 5 is a positive, times 2 plus a negative 5 would be a negative, and that answer would give us a negative when we take a positive times a negative. When we take, let's say we take 0. So if I put in 2 minus 0, that's a positive, times 2 plus 0, that's also a positive. And a positive times a positive is a positive. Well, that fits because we need greater than or equal to 0. Let's check our third spot. If we use, let's say, 5. 2 minus 5 is negative, 2 plus 5 is positive, and a negative times a positive is negative. So the only area that works in this case is between negative 2 and positive 2, and it is an or equal to problem, so those values are included. So when we write that, again, we can write x such that negative 2 is less than or equal to x, less than or equal to 2. And again, that's probably one of the easiest ways. If you write it in interval notation, we use brackets because those endpoints are included, and we just go from negative 2 to positive 2. So this is two different ways of writing the same thing. Finally, we've got a fraction and a radical. So first of all, the denominator can't be equal to 0, and secondly, t minus 2 has to be positive, or t minus 2 can't be negative. So t minus 2 has to be greater than or equal to 0, but then we can't let it equal 0 either because it's in the denominator. So we actually change this to t minus 2 is simply greater than 0, and this one's very easy to solve. We add 2 to both sides, and that gives us t is greater than 2. So again, we can write it as t such that t is greater than 2 in set notation, or in interval notation, our smallest value you can use is 2, and that's not included. It has to be just greater than 2, and then we go all the way until we can go forever to the right, to any values greater than 2. So implicit domain, the key things you have to look for is you can't let denominators equal 0. You can't let inside of a square root or any even index for a radical be negative, because you can't take the square root of a negative number.
There are four main methods of representing a function: verbally, using words; algebraically, with a formula; visually, using a graph; and numerically, using a table. The main ones we'll focus on is algebraically, using a formula, and then also visually, using a graph. These are the most useful for us because in one we have the formula, and in the other one we can get a picture of what's going on. Your assignment is assignment 17. It's listed here from section 3.1, pages 221 and 222. The numbers are listed there, and if you have questions on these, you can ask me tomorrow during class. Have a good rest of the evening.